You ever hear a statistic, like the average salary for a job or the average rating for a movie, and you just think to yourself, that can't be right. It just doesn't feel like the real story. Well, you're not wrong. Today, we're going to pull back the curtain on why the average can be one of the most misleading numbers out there, and how its best friend, variation, is what really gives you the full picture.
So, let's just get right to the heart of it with a question. Picture two different classes. They both take the exact same quiz, and what do you know? They both get the exact same average score. So, does that mean the students in both classes basically had the same experience? Not even close. And this right here shows you the problem perfectly. Okay, look at Class A. Every single student scored a 3. That is the average. So you've got a perfectly consistent result. Now check out Class B. Their average is also a 3, but the reality is totally different. Here you've got students who are either really struggling, scoring a 1, or totally crushing it with a 5. Nobody is average. This is exactly why we need to measure not just the center of our data, but also how spread out it is. Okay, so how do we actually measure this spread? Well, the first and simplest tool we can grab is something called the range.
The range is pretty much what it sounds like. You just find the highest number in your data, find the lowest number, and subtract the two. So for our quizzes, Class A has a range of 0, because everyone got the same score. Class B, on the other hand, has a range of 4. It's simple, it's intuitive, but as you're about to see, it has a huge weakness.
Wow, this slide tells you everything you need to know about the problem. It's a real-world story. A data analyst was looking at an Army database and saw the age range for soldiers was from 4 years old to 107. I mean, come on. Obviously, there wasn't a toddler or a centenarian doing push-ups. Just two single bad data points, typos, completely blew up the range. It just shows you how easily outliers can throw the whole thing off. It's not a stable measure at all.
So, if the range is too shaky, what do we do? For a much more robust and reliable picture of variation, we need to turn to what the pros use, the standard deviation. Think of variance and standard deviation as a dynamic duo. You can't really have one without the other. See, to get the standard deviation, you first have to figure out the variance. Now, all variance is a measure of the average squared distance of every single data point from the middle, from the mean. Then, we just take its square root to get the standard deviation. And that gives us a number that makes a lot more sense. It tells us the typical or standard distance that any given point is from the average.
Now, the calculation might sound a little scary, but it's actually a super logical 5-step process. First, find the center. That's the mean. Then you measure how far each individual point is from that center. After that, you square all those distances. That's a neat trick to make them all positive. Step 4, you find the average of those new squared distances. And finally, you just take the square root to get everything back to normal. Let's actually walk through it.
All right, let's get our hands dirty. Imagine we're tracking the wait times for 6 patients at a clinic. Their times are 2, 3, 3, 8, 10, and 10 minutes. So, step 1, find the mean. We add them all up. We get 36. We divide by our 6 patients and boom, the average wait time is 6 minutes. Simple enough.
On to step 2. How far is each patient's wait from that 6-minute average? Well, the first patient, who only waited 2 minutes, was 4 minutes below the average, so their deviation is -4. The patient who waited 8 minutes was 2 minutes above the average, so their deviation is a +2. And we just do that for all 6 patients.
Okay, now here's the problem. We've got all these negative numbers. If we just added everything up right now, the negatives and positives would start canceling each other out, which we don't want. So statisticians came up with a really clever trick. Step 3 is to square every single one of those deviations. So -4 times -4 is +16, and +4 times +4 is also +16. Just like that, this one simple step gets rid of all the negative signs so we can move forward.
So now we add up all those new squared numbers, the 16, the 9, the 9, and all the rest, and we get a grand total of 70. This number actually has a special name. It's called the sum of squares. It represents the total squared variation inside our data.
For step 4, we need to find the average of that squared variation. Now here's a little statistical tweak. When we're working with a sample of data, not the whole population, we divide by the number of patients -1. So 6 minus 1 is 5. So we take our 70, we divide it by 5, and that gives us our variance 14.
And now for the grand finale, the last step.
We take the square root of that variance, the square root of 14, to get back to our original units, which were minutes. And the square root of 14 is 3.74. So here's the big takeaway. While the average wait time is 6 minutes, the typical, or standard, deviation from that average is about 3.74 minutes. We have such a richer story now.
So great, we have calculated this powerful new number. But what do we actually do with it? How does it help us make decisions in the real world? Well, this is where it all starts to click.
One of the absolute coolest things we can do is compare the consistency of two totally different things using a tool called the coefficient of variation, or CV. All it does is take the standard deviation and express it as a percentage of the mean. This basically levels the playing field, creating a relative measure of spread that lets us make real apples-to-apples comparisons.
Let's see it in action. For our lab, Lab A, that standard deviation of 3.74 is 62% of our 6-minute mean. Okay, now let's say we have a competitor, Lab B. Their average wait is longer, it's 8 minutes, and their standard deviation is also a bit bigger, at 4 minutes. But when we calculate their CV, their standard deviation is only 50% of their mean.
So, which lab is more predictable? Which one performs more consistently? It's Lab B. Even though their average wait is longer, their lower coefficient of variation, 50% compared to our 62%, tells us their process is more stable. Their wait times are more tightly packed around their average, which makes them more predictable.
But wait, there's more. Variation also gives us some serious predictive power, thanks to this amazing rule called Chebyshev's theorem. It's basically a guarantee. It tells us the minimum percentage of data that has to fall within a certain distance from the mean. And the best part is, it works for any data set, no matter how weird or lopsided it is.
So here's the practical part, what this really means. Chebyshev guarantees that for any data you have, at least 75% of all your values will be within 2 standard deviations of the mean. Go out to 3 standard deviations, and you're guaranteed to capture at least 89% of your data. It gives you a powerful, reliable baseline for understanding where most of your data lives.
All right, so after all of that, all these calculations and concepts, what's the big idea? What should we really be walking away with here?
Okay, let's just boil it down. First, and most importantly, averages by themselves are only half the story. They can be really misleading. Second, the range is a super simple way to start looking at spread, but remember, it's just not very stable. Third, standard deviation is the real deal. It's the robust, gold standard way to measure how data clusters around the average. And finally, once we have that, we can use amazing tools like the CV to compare consistency and Chebyshev's theorem to actually predict outcomes.
So the next time you hear a number, a statistic, just presented as a single, simple average, you'll know better. You'll know to ask the single most important follow-up question you can ask. But what's the story of the spread?